In section 4.6, we look at inverse trigonometric functions. But first, we have to review inverse functions from an algebraic perspective. So let's remember that a function f takes a set of numbers here called the domain, and if we pick one of the numbers in that domain, call it x, the function f will send that value of x to a value that we call f of x. And sometimes we'll give this an abbreviation y. So we know that y is equal to f of x. The inverse of a function is the function that will undo whatever the function did. So the inverse function will take this value over here, which I will call y for short, and it will send it back to where it came from. And so in that way, we will say that f inverse of y is equal to x. So an inverse function simply undoes whatever the function did. A couple of important notes to make is that in this diagram here, this first set is what we would call the domain of the function f, and the second set is what we would call the range of the function f. So again, the function takes values in this set and assigns them to values in this set. The inverse function does the opposite. The inverse function starts here and assigns those values to a value over here. So from the inverse function perspective, this set over here is the domain of that one, and this set is the range of that one. So to put it simply, the domain of the function is the same as the range of the inverse, and the range of the function is the same as the domain of the inverse. Let's take a look at a simple algebraic example. In the first example, we have a function defined by the equation f of x equals 2x minus 3. We want to find the equation that represents the inverse of f. So there is a procedure to doing this, and this is review from algebra. So when we start with f of x equals 2x minus 3, let's remember that f of x is another name for y. So y is equal to 2x minus 3. What an inverse function does is it simply inverts the x's and the y's. So if I want to find the inverse function, the y becomes an x, and the x becomes a y. So this equation right here is the equation that represents the inverse. Now what we typically do with that second equation is we will solve it for y. So if I add 3 to both sides and then divide by 2, we get x plus 3 divided by 2 is equal to y. Now what I'm going to do is put those side by side. So again, we started with the equation y equals 2x minus 3. And when we found the inverse of that equation, we got y equals x plus 3 divided by 2. Now what I'd like to do is just take a moment to verify that these functions are inverses from a very simplistic point of view. Let's think about those sets of numbers. So here I have the domain of the function f, and over here is the range of the function f. And I'm going to pick a random value in that domain. I can select any value of x that I want. I'm going to select x is equal to 5. The function will take that value of x and it will assign it to a value that we're going to call f of 5. And to get f of 5, we can simply plug the value into the original function. So the original function was f of x equals 2x minus 3. This means that f of 5 is 2 times 5 minus 3, and this value is 7. So a short way to represent this would be that the function f takes the value 5 and assigns it to the value f of 5, which we now know is 7. Now, if this second equation is truly the inverse of the first one, then when I apply that rule, coming back this way, okay, so this is the inverse rule, and this was the original function. The inverse rule should take 7 and send it back to 5. So when you look at the second rule here, if you plug in x equals 7, you're going to get y is equal to 7 plus 3 divided by 2. That's 10 divided by 2, and that is 5. And this will happen with any value of x that you choose. So now again, just to make sure we fully understand the concept, let me make a table of values. So here I have the original function y equals 2x minus 3, and I've picked some random values of x to plug in. If you plug in x equals 5, we get y equals 7. X equals 0 gives us y equals negative 3. X equals 1 gives us y equals negative 1. X equals 2 gives us y equals 1. And finally, x equals negative 3 will give us y equals negative 9. If you want, you can pause and verify that this is true. But the main concept is this. If this equation truly represents the inverse of this one, then when I plug in all of these values of y into x for this equation, it should reverse these coordinates. So in other words, if I plug in x equals 7, I should get y equals 5. And we can verify that, right? If x is 7, 7 plus 3 is 10, 10 divided by 2 is 5. If I plug in x equals negative 3, notice that you get negative 3 plus 3, which is 0. If I plug in x equals negative 1, we get negative 1 plus 3, which is 2, divided by 2, which is 1. If I plug in x equals 1, 1 plus 3 is 4, divided by 2 is 2. And finally, if I plug in x equals negative 9 plus 3 is negative 6, divided by 2 is negative 3. So you should notice that in this table, it's simply all of these points here, but reversed. That's what an inverse function does. Now, what we can do in addition to this is we can graph these two equations on the same set of axes, and we can observe a relationship there as well. So here we have the original function f of x is equal to 2x minus 3, or we can also say y equals 2x minus 3. And then here we have the inverse of that, which is y equals x plus 3 divided by 2. And I want you to notice that if you draw the line y equals x, that line will come down right through the middle and will provide symmetry between these two graphs. So in other words, if we outline some points here on the first graph, like this point here is 0, negative 3, this point here is 1, negative 1, here we have the point 2, 1, here we have the point 3, 3, and up here we have the point 4, 5. I want you to notice that if you look at these points on the other graph, you will notice that all of the coordinates of those points will be reversed. So this point here is negative 3, 0, which is the reversal of this point here. This point right here is the point negative 1, positive 1. Here we have 1, 2. This point is 3, 3 still, right? Because if you reverse 3 and 3, you still get 3 and 3. And this point here is 4, 5. And what you should be able to see is that we have nice symmetry across that line. So these points all line up. This will always happen when you graph two equations that are inverses of each other. Let's take a look at a second example. So our next equation is y equals x squared minus 2. I want to find the equation of its inverse, and then we'll take a look at their graphs. So I start with y equals x squared minus 2, and the way we get the inverse is we switch x and y. So y becomes x, and x becomes y. And if you do that, you get x equals y squared minus 2. This is the inverse equation. Now, solving for y here is a little bit tricky because you have a square. It can be done, and I'll talk about that in just a minute. But I want you to notice what happens to a table of values with these two equations. So here I have the first equation, and I have chosen 3 values of x randomly. If I plug in x equals 0, we get y equals negative 2. If I plug in x equals 1, we get y is negative 1. And if x is 3, we get y is 7. In the other equation, look what happens here. If I pick this value of y and plug it in for x, we have to figure out what y would be equal to. Well, if I plug in x equals negative 2, we get negative 2 equals y squared minus 2. And if I add 2 to both sides, we get y squared equals 0. And this means that y is 0. So you can see that that first point gets reversed. No problem. If I plug in x equals negative 1, it's a little bit different. Plug it in negative 1, we get negative 1 equals y squared minus 2. Adding 2 to both sides gives us 1 equals y squared. And then taking the square root of both sides, this is going to end up giving us y equals plus or minus 1, right? Because 1 squared is 1 and negative 1 squared is 1. So you get 2 values for y there. Now, that's okay when you're talking about inverses, but that's not okay when you're talking about functions. And we'll come back to that in just a couple minutes. If y is 7, that's going to correspond to x equals 7 in the second equation. And if I let x equals 7 in the second equation, we can solve for y. And you'll notice, once again, we get 2 values for y. We get positive or negative 3. So this is a little bit of an issue. Let's take a look at the graphs to see what's going on here. So I'm not going to take time to go through and painstakingly graph each one of these, but I will just show you that the original equation, y equals x squared minus 2, is this parabola here. And the inverse equation, x equals y squared minus 2, is this parabola here. And you can see, once again, we do have symmetry across this line, y equals x. You can see that symmetry in multiple places. For example, this point here lines up perfectly with this point here as a mirror image. There's a point here which lines up with a point over here. Perfect mirror image, etc., right? You can see it all the way through. So you definitely have a mirror image of one. Each one is a mirror image of the other across that line. But there is a little bit of a problem with this. In mathematics, we don't like any kind of equation. We like functions. And the problem is, this graph right here does not represent a function. So I don't know if you remember this or not from algebra, but when you have a graph that is sideways like this, when you draw a vertical line, you will hit that graph in 2 spots. And so what happens there is, if I pick a value of x here, the function gives us 2 different y values. We get a y value up here, I'll call that y1, and we get a y value down here, which I'll call y2. And this can't happen when you have a function. When you have a function, when you plug in a value of x, you get a single value for y. So the reason this happened is because our original function, this function here, is not a one-to-one function. So let's talk about one-to-one functions next. Again, this is review from algebra, but a one-to-one function is a function where every element in the range comes from exactly one element in the domain. All right, so what does that mean in terms of graphs? Well, to be a function, we know that when you draw vertical lines, you are only allowed to intersect the graph one time for every possible vertical line that you can draw. And so you can see that these are both functions because every vertical line only hits the graph one time. But to be a one-to-one function, not only do vertical lines have to hit the graph at the most one time, but horizontal lines also are only allowed to hit the graph one time. So if you imagine drawing every possible horizontal line, you can see for this first graph, every possible horizontal line only intersects the graph at the most one time. So this graph here represents what we would call a one-to-one function. However, for the other graph, you can see right away that when you draw a horizontal line, that is going to intersect the graph more than once. And it only needs to happen one time. However, for this graph, it happens many times, right? All of these horizontal lines intersect the graph more than once. So when this happens, we say that it is not a one-to-one function. Now, why does that matter? Well, it matters because when the original function is one-to-one, the inverse will also be a function. But when a function is not one-to-one, the inverse will not be a function. And so let's go back to the previous page here. The reason we had an issue with this problem here is because our original function, y equals x squared minus 2, is not one-to-one because horizontal lines hit it more than once. Well, what that means, when you find your inverse, the inverse just takes that parabola and turns it sideways. So now vertical lines are going to hit the graph more than once. And that's a problem because if vertical lines hit the graph more than once, it's not a function. So when we're talking about inverses, we want both of our functions to be, we want both of our equations to be functions. We want the original one to be a function, and we want the inverse to also be a function. And this will only happen if the original function is one-to-one. So when talking about inverse functions, it is a requirement that your original function is one-to-one. And I have this summarized here. If y equals f of x is a one-to-one function, then the inverse of f is also a function, and it can be denoted as y equals f inverse of x. Now, I know you've probably seen this notation before. Let's remind ourselves that the notation f with a -1 exponent does not represent the reciprocal of f. In other words, f inverse does not mean 1 over f. Okay? It is not like exponents in the way that you're thinking about exponents from the past. This symbol, this -1 power, represents an inverse. So again, this is just emphasizing the fact that we want our functions to be one-to-one so that the inverse will also be a function. Now let's see how this applies to trigonometry. So we start with the journey of finding the inverse of the function y equals the sine of x. So here I have graphed y equals sine of x. And you can see very clearly that this is not a one-to-one function. If I draw a horizontal line, you will see that it intersects the graph infinitely many times. So if I were to try to find the inverse of this graph, this is what it would look like. So here I have my original graph of y equals sine of x, and we know that the inverse has symmetry through the line y equals x. So I want you to notice that you have a mirror image across this line here. And so this green graph here would represent the inverse of sine. But there's a big problem with this. The big problem is this is not a function, and we really want this to be a function. So to make this work effectively, what I need to do is I need to go back to my sine graph, and I need to restrict the domain so that this will be one-to-one. So if you think about that for just a minute, in order for this to be a one-to-one function, let's suppose we start down here. When we come up to this high point, we have to stop. If we repeat ourselves after this point, then you will have horizontal lines intersecting the graph more than once. So to make the sine a one-to-one function, what we have to do is restrict the original domain to only be the values in between negative pi over 2 and positive pi over 2. And here is what that graph will look like. So what I have here is the function y equals sine of x. X is restricted to only be values between negative pi over 2 and positive pi over 2. And you'll notice that the y values are still in between negative 1 and positive 1. But now we can find the inverse of that function. So let's go ahead and take a look at what that is. So to get the inverse of y equals sine of x, we are going to switch x and y. So we get x is equal to sine of y, and then we are going to solve for y. And the way we solve for y is we are going to assume that we have an inverse function that exists. We will take the inverse sine of the left-hand side, and that should be equal to the inverse sine of the right-hand side. And basically what happens here is the inverse sine and the sine cancel each other out, and we get y is equal to inverse sine of x. Now, just like I mentioned earlier, when you have a function, such as y equals sine of x, the domain of the function becomes the range of the inverse function, and the range of the original function becomes the domain of your inverse function. So for the inverse function, x will have to be a value between 1 and negative 1, and y will always be a value between negative pi over 2 and positive pi over 2. And let's go ahead and bring in the graph to see what it looks like. And so here it is. We have the original graph, y equals the sine of x, which is right here. And you can see that x is between negative pi over 2 and positive pi over 2. Y is between 1 and negative 1. And then the inverse function, if you were to graph it, would look like this. And you can see that you have that symmetry across the line y equals x. And for the inverse graph, you can see the range is all the values between pi over 2 and negative pi over 2. And the domain is all the values between 1 and negative 1. Let's talk about cosine. To find the inverse of cosine, we have the same problem. The cosine graph is not a one-to-one graph. If you draw any horizontal line, you are going to hit the graph many times. So what we do for cosine is we erase all the negative values of x, And we also erase all the values of x past pi. So for y equals cosine of x, we restrict the domain to only be the values between 0 and pi. And you can see if we do that, starting at 0, going to pi, we now have a one-to-one function. Every horizontal line you draw here will only hit the graph one time. The y values for this are all the y values between -1 and +1. So now we can go ahead and talk about the inverse function. The inverse function, of course, will be y equals inverse cosine of x. And for this, we know that x has to be a value between -1 and +1, and y has to be a value between 0 and pi. And let's bring in that graph. And so here's what it looks like. We have our function y equals cosine of x here with the restricted domain. And the inverse cosine is this other graph here. Once again, you can see that we have symmetry across the line, y equals x. Now, I don't want you worrying too much about these graphs. You're not going to have to graph inverse functions. I just want you to see that indeed it does have that graphical relationship. Let's take a look at tangent. So here we have the graph of y equals tangent of x. Again, we have the problem that tangent is not a one-to-one function. If you draw a horizontal line, you will intersect the graph of tangent many, many times. So what we do is we just focus in on the part of tangent between -pi/2 and +pi/2, and we simply erase everything else. So if I erase everything except for that piece of the tangent graph, what I'm doing is I'm restricting my domain of tangent to be all the values of x to be strictly between -pi/2 and +pi/2, and the y values for tangent are between -infinity and +infinity because it goes up and down forever, right? And now we can define the inverse tangent to be the function whose domain is all real numbers, but whose range will only be values between -pi/2 and +pi/2. And we can also bring in that graph. And so here we have the graph of tangent, which is this graph here. And here is the graph of inverse tangent. And again, you have symmetry across the line y equals x. But again, don't worry too much about the graphs. I just like showing those to you so you can see that indeed it does have that symmetry. Now let's summarize everything that we said and do some examples. So here are the definitions for the inverse sine, inverse cosine, and inverse tangent. So we define y equals inverse sine of x to mean that x equals sine of y. Y has to be in between -pi/2 and +pi/2. By the way, there is another way to talk about inverse sine. We call that the arc sine. Don't worry about this. These mean exactly the same thing. We just have two different notations that mean the same thing. For inverse cosine, it's very similar. Y equals the inverse cosine of x if x equals the cosine of y, and y has to be between 0 and pi. And finally, y equals inverse tangent of x means that x equals tangent of y, and y has to be between -pi/2 and +pi/2. The important thing to pay attention to here is this. The inverse function y equals inverse sine of x will only give you an angle between -pi/2 and +pi/2. The function inverse cosine of x will only give you an angle between 0 and pi. And the inverse tangent function will only give you an angle between -pi/2 and +pi/2. So a couple of things there. One, of course, is to memorize what range of values it gives you in terms of its angles. But the other is this. Anytime you see an inverse trig function, you need to understand that this just represents some angle. And so to help you just kind of understand this on a very fundamental level, let me write down a very simple equation. You know that the sine of 30 degrees is equal to 1/2. This is something that we learned long ago. In radians, this means the sine of pi over 6 is equal to 1/2. So the basic idea is you take a trig function of an angle, and that is going to give you the ratio. That's the main idea with trigonometry. The inverse trig function reverses that relationship. So the way you would say this using inverse trigonometry is you would say the inverse sine of 1/2 is equal to pi over 6. It simply reverses the thought process. So the important thing here is you have the inverse sine of some ratio, some value, and you are getting an angle out of it. So anytime you apply an inverse trig function, you are talking about an angle. Let's take a look at these examples. So for this first problem, it says, evaluate in radians without using a calculator. What is the inverse sine of 1/2? Now, we just talked about that down below, but how would you do this? Well, first of all, you have to understand that this is going to give you an angle. The second thing you have to understand is where is that angle going to be? Well, for inverse sine, it tells you that that angle has to be a value between negative pi over 2 and positive pi over 2. So if you look at angles in standard position, negative pi over 2 is down here, positive pi over 2 is up here. That means that that angle has to be somewhere in between those two values, which essentially means that you're either talking about an angle in the first quadrant or you're talking about an angle in the fourth quadrant. Well, in the fourth quadrant, we know that sine is negative. So the fact that we're talking about the inverse sine of positive 1/2 tells us that this angle must be in the first quadrant. So if I draw a picture of what that angle might look like, let's call it theta. What we know is that the sine of this angle is 1/2, right? Because it says that right here. Inverse sine of 1/2 means the angle whose sine is 1/2. Well, sine of theta is opposite over hypotenuse, so we know that this missing side here is radical 3, and we recognize that this is a special triangle where theta is 30 degrees, and 30 degrees, of course, is pi over 6. So the inverse sine of 1/2 is pi over 6. This is how you could figure it out if you didn't already know that fact from down below, from our discussion down here. But the important thing is when you draw your picture for that angle, you have to draw it in the correct quadrant. You can't draw it in the second or third quadrant because inverse sine doesn't give you an angle in the second or third quadrant. Let's take a look at the next one. So in the next problem, we have arc cosine of negative radical 3 over 2. Again, this is equal to some angle. So the first question is, where is it? Where is that angle? Well, for inverse cosine, we know that it will only produce an angle between 0 and pi. So if you look at your x and y axis, here's the angle 0, here's the angle pi over 2, here's the angle pi. If the angle is between 0 and pi, it has to be somewhere in either the first quadrant or the second quadrant. Well, in the first quadrant, cosine would always give you a positive value. In the second quadrant, cosine gives you a negative value. So the fact that we have a negative radical 3 over 2 tells us that our angle must be in the second quadrant. So if I draw a picture of what that angle might look like, here's that angle theta, we know that the cosine of this angle is negative radical 3 over 2. Cosine is the adjacent side over the hypotenuse. We recognize this triangle and we know that this opposite side over here is equal to 1. So again, we know that this angle is 30 degrees. Well, that means that theta is 150 degrees. And 150 degrees is 5 pi over 6. So what is the arc cosine of negative radical 3 over 2? Well, it's 5 pi over 6. Because the cosine of 5 pi over 6 is negative radical 3 over 2. And for our last example here, we have the inverse tangent of negative 1. Once again, inverse tangent is an angle. So the first question is, where is it? Well, inverse tangent always gives you an angle between negative pi over 2 and positive pi over 2. So if you draw a picture of that, that means the angle is going to be somewhere in here. So it either has to be in quadrant 1 or quadrant 4. Well, you have inverse tangent of negative 1. So we know that it has to be in the fourth quadrant because tangent in the first quadrant would have been positive. So the fact that this is a negative value tells us that we have to be in the fourth quadrant. Well, if theta, your angle, equals inverse tangent of negative 1, that's the same thing as saying tangent of theta equals negative 1. And that means in this right triangle, the opposite side divided by the adjacent side has to equal negative 1. So that would be negative 1 over 1, which means the missing side is radical 2, and you should all recognize that this angle here is 45 degrees. So what is this angle here, theta? Well, it's going in a clockwise direction, so it would be negative 45 degrees, and negative 45 degrees is the same as negative pi over 4. So the inverse tangent of negative 1 is negative pi over 4. Now, I know that this could be a little bit overwhelming and a little bit confusing when you're first learning it, but just keep in mind that all you're trying to do is find the angle for which these things are true. And then the other important thing is that angle has to be in a certain quadrant. It has to be between certain values. So again, in the definition, what you want to focus on when you're memorizing this is focus on the trig functions themselves, the inverse functions, and where they give you angles. Now, once again, just a quick note about inverse functions. So when we say inverse sine of x, keep in mind that that does not mean 1 over sine of x, right? So this negative 1 right here is not an exponent, even though it looks like 1, okay? Instead, it means inverse. All right, this next example is relatively simple. It says use a calculator to evaluate each expression to the nearest tenth of a degree. So to do this, you simply have to plug it into your calculator. Now, they can ask you for these in either degrees or radians. In this one, they ask for it in degrees. So for that, you want to make sure your calculator is in degree mode. And all you have to do basically is type these in. So for part A, we have arc sine of 0.5075. When you type this in on your calculator, you are going to hit the second key, and then you will hit the sine key because the inverse sine is above that key. And then you'll simply type in the value, which is 0.5075. And after you do that, hit enter. And if you round this to the nearest tenth of a degree, this one here is 30.49744, and that is approximately 30.5
degrees. Same thing for the second one. If I take the arc sine of negative 0.5075, you do the exact same thing. You just type it in with a negative sign. And for this one, you'll see that you get negative 30.49744. And this is approximately negative 30.5 degrees. And it works the same for the rest of them. So what I'm going to do is just put in the answers for all of these, and then you should double check it on a calculator. All right, so here they are. So inverse cosine of 0.6428 is approximately 50 degrees, or 50.0 degrees to the nearest tenth. Inverse cosine of negative 0.6428 should be 130.0 degrees when rounded. Arctangent of 4.474 is approximately 77.4 degrees. Arctangent of negative 4.474 is approximately negative 77.4 degrees. Double check those on your own to make sure that you know how to use your calculator properly. Now we're going to take a little bit more of a theoretical problem. It says to evaluate this expression without using a calculator. So we want to take the sine of the inverse tangent of 3/4. And this can be a little bit overwhelming, but instead remember what I told you about inverse trig functions. The inverse tangent of 3/4 is an angle. Let's give it a name. Let's call it theta. So all I want to find in this problem is the sine of that angle theta. What is that equal to? Well, what we need is a picture of theta. So if I'm saying that this is theta, then what I'm saying is theta equals inverse tangent of 3/4. And we know that theta has to be an angle between pi over 2 and negative pi over 2 because of the inverse tangent definition. Well, because it's positive, it has to be in the first quadrant. So here is theta. And what we're really saying here is tangent of theta equals 3/4. So if I label the sides, the opposite side is 3, the adjacent side is 4, and by the Pythagorean theorem, the hypotenuse would be 5. Now all I have to do is find the sine of theta, and this is incredibly easy because we have a picture of theta. We know that sine is opposite over hypotenuse. And so this is going to be equal to 3/5. In our last example, it's essentially the same as the last problem. In this case, we have the sine of the inverse cosine of x, and they tell us to assume that x is positive. We want to know, what is this equal to? Well, inverse cosine of x is an angle. Let's give that angle a name. Let me call it theta. If I do that, then I am just looking for the sine of theta. So what is that equal to? Well, let's draw a picture of theta. Theta is the inverse cosine of x. Now they tell us that x is positive, and that means that theta has to be in the first quadrant. And if theta equals the inverse cosine of x, that's the same thing as saying the cosine of theta is equal to x, which is x over 1. But cosine of an angle is the adjacent side divided by the hypotenuse. So the adjacent side would be x, and the hypotenuse would be 1. And we can solve for this missing side, let's call it a, by saying x squared plus a squared is equal to 1 squared. Subtracting x squared gives us a squared equals 1 minus x squared. And if I take the square root of both sides, we get a is equal to plus or minus the square root of 1 minus x squared. But we know this is going to be positive because, again, we are in the first quadrant, and all values are positive in the first quadrant. So this missing side of the triangle is the square root of 1 minus x squared. Now, as soon as we have that, we're ready to finish the problem. We are looking for the sine of theta. look at your picture. Here's your angle theta. Sine of an angle theta is the opposite side divided by the hypotenuse. And in this case, that is the square root of 1 minus x squared divided by 1, which is the square root of 1 minus x squared. So again, the important thing to remember is that inverse trig functions are angles. Remembering that fact will help you understand the concept.